All right, so briefly, while Roger is queuing up the video, this is a video about a new paper, and what these people took on is a very interesting idea, which is that when you train a neural network, you have various hyperparameters depending on which optimizer you use, learning rate for pretty much all of them, but then some other parameters, you know, an alpha, a lambda, this or that, or whatever. And so they said, well, why can't we just train a computer to figure out those parameters, and not only fixed parameters, but maybe even changing them over time. So if you're familiar with like learning schedules, warm up and things like that, why don't we just train a computer to figure all that stuff out? So they trained a whole lot of models, and they tried to build something that could then monitor what was happening in the training, and so that you don't have to actually select any hyperparameters. And it's not really the selecting hyperparameters, but it means that you really only need to run the training once instead of running it maybe 30 times trying to find the best hyperparameters. So that's the general gist of this paper.
Ted, is it how should I think of it? Does this replace the whole SGD thing, or is it providing hyperparameters to an optimizer?
So to a limited extent, assuming it does a really great job, right? You don't need to decide if you're going to use Atom or one of the flavors of Atom or SGD or MSProp, and you don't need to decide any of the hyperparameters. You literally just train it once, and it should be optimal-ish.
And it then replaces Atom?
It is the
or
optimizer.
Uses Atom.
It is an optimizer, but it is an optimizer that instead of just using some like mathematical formula like momentum, right, is an optimizer that has seen millions of neural networks trained.
Okay.
And it's going to adaptively decide, oh, I think I need to do this right now. I think I need to do that right now. And so then you don't ever give it hyperparameters. You just say, use my smart optimizer, train my model once.
Got it. Okay. And so my understanding is like Atom, the parameter sizes associated with Atom are bigger than the models. Is that, do I understand that correctly?
That's the memory footprint.
Yeah, the memory footprint, right.
Right. But the bigger thing is if it takes you 4 GPU years to train it and you need to run it 30 times.
Hey, Ted.
Well, yeah, it depends which, yeah, that's true. But it also depends.
Let me interrupt here. Ted, we've sent you a couple of messages. Can you, since you're the host.
Sorry. No, Roger's the host.
So. Roger's the host.
Yeah.
Oh, okay. Roger, can you kill Thomas if you could?
Yeah.
Thank you.
Okay.
Thank you, sir.
Yeah, so I guess that, and maybe I should just wait for the movie here, but I was wondering about the memory footprint of this one, of VeLO as well.
I don't remember the details. They made the model itself very small, but
oh, did they?
They made the model small, but I don't remember. It's still probably keeping track of a lot of things per parameter. So yeah, I think they talk a little bit about what's the memory footprint.
Okay. All right, we can just go ahead and start then.
Full of coffee beans or tea leaves to fill your cups with the
sound and everything okay?
It's kind of quiet. Can you turn your computer volume up?
Yeah. There you go. Thank you.
Of productive work.
Better? Was that okay?
Yeah, that was much better.
Much better.
Speaking of work, do you know what does the heavy work for us when training neural networks? Yes, it's optimizers like stochastic gradient descent or Atom that decide how much to update the weights of a neural network during training. Only that they need the right hyperparameters to work well, and who knows whether to set the learning rate to 0.01 or 0.0001, right? Well, you do not need to bother about optimizer hyperparameters again, because new work proposes VeLO, a neural network trained to act as an optimizer that says goodbye to hyperparameters. It can dynamically decide what are the best weight updates for your problem and for your current training step. It sounds almost too good to be true, right? In this video we will explain the VeLO paper, what VeLO's limitations are, and we will find out how a neural network can behave like an optimizer and how it was trained. But not before we thank Cohere for sponsoring today's video. Since you're watching this video, we assume you already heard about the incredible advancements of natural language processing. Maybe you thought of including the latest and greatest large language models in your applications. Well, then Cohere is the right thing for you. It lets you use extremely capable language models to let them classify text for you. Use Cohere. Just install developer tiers to the optimizers that update the weights of a neural network during training. The optimizer determines a new, hopefully better weight for a neural network by adding or subtracting a certain value from it. The SGD optimizer determines this value to be a fraction of the gradient of the loss with respect to the weight. This basically means that we should go a step into the direction of steepest descent to minimize the loss. One very important decision that the optimizer takes is to determine how far to move into the direction that minimizes the loss. If it goes too far, it can overshoot a minimum. If it goes too little, the neural network training will take forever. Here, by using this step size as an example, we basically explained the learning rate hyperparameter of SGD. Other optimizers do even more complicated things than that. For example, they use momentum, in which the weight update of the current step uses some component of the update direction from the previous update step. But it is not a topic of today's video to give an overview about the entire zoo of optimizers. But keep in mind that there are a lot of them and there are a lot of strategies to do the weight updates. Even worse, each of these little strategy comes with a hyperparameter that decides how much of this little hack should act at a certain time step during training. For example, the learning rate can vary during the training run, and you have to decide upon a learning rate schedule. So it is hard to manually decide what is the best strategy to update the weights for each neural network and for each different dataset. Therefore, to see how well a set of hyperparameters do, one needs to do one whole training run of a network, see how low the loss gets. Then change the hyperparameters and do yet another run, and then another configuration and another, and so on. And this becomes really expensive really fast, until finally, after tens or even hundreds of runs, we can take the set of hyperparameters that we saw performed best. But don't worry, because this paper proposes VeLO, which is a learned optimizer that can do the important decisions on its own and does not have any hyperparameters. The idea of this paper is to do meta-learning. We can use training runs of different architectures and datasets to teach a neural network to act as an optimizer. The network would take weight and gradient information and predict how to update the weights to minimize the loss of the target neural network. Of course, this idea is not new. Learned optimizers have been here for around a while, but no one has trained optimizers at this scale before and for this range of tasks, going towards a more general purpose optimizer that can be used out of the box for many datasets and applications. So how does it work? What do the authors need to do to train the VeLO neural network to act as an optimizer for other neural networks? First, they need to assemble the training dataset for VeLO, consisting of models of different model families, such as multilayer perceptrons, convolutional networks, residual networks, transformers, recurrent neural networks, autoencoders, variational autoencoders. And these all have different depths, layer widths, and activation functions. To augment the data, the authors even do things like reparameterizing the weights or changing the floating point precision. These models are to be trained on tasks ranging from image classification to image generation, text generation, and training learned optimizers. Keep in mind that the variety of models and tasks captured by this training data for VeLO, because the variety in the training data is highly likely to determine its capabilities at test time, because models usually perform well on the type of settings they have already seen in training and fail to generalize on tasks out of distribution. No spoilers, more about this later in the video. And VeLO acts like this for every single weight, so for each scalar in the target neural network which it aims to optimize, at each time step it predicts how much to subtract from the weight to update it. We say here subtract, but of course that if it decides to subtract a negative value, it is like it would have added something to the weight. That VeLO applies to each single weight of the neural network it optimizes comes with the advantage that in this way it can be applied to any neural network independently of its architecture and number of parameters. But the downside is that it can become really costly to apply VeLO as the number of weights increases in a network. Therefore, the authors strive to keep VeLO really small. The lightweight architecture of VeLO is composed of a per tensor network and a per weight network as follows. The per tensor network is an LSTM which takes information about a parameter tensor. In this way, the authors make sure that when VeLO predicts an update value for each parameter, the update is informed on other weights of the network. As input, the authors use, we cite, the mean and variance of parameter values, the exponential moving averages of the gradient and squared gradient as used in the Adam update. The per tensor network also takes as input a series of additional features representing the current fraction of training completed, so it can learn training time-dependent strategies, such as learning rate schedules. Finally, our per tensor network has access to the training loss, which can enable complex behaviors, such as detecting divergence of the loss. Then the LSTM predicts the weights of a subsequent network, the per weight network, which is a multi-layer perceptron, or MLP in short. This MLP is also extremely small, of just 2 hidden layers with 4 hidden units. This is the one that uses per weight information such as gradients and the value of the weight as input to predict the update for that weight. Previous work from the same authors did this differently, and the MLP took weight information and also the hidden representation delivered by the LSTM and learned its own weights. But this made the MLP's input larger, therefore slower. So the authors decide for the LSTM to train to deliver the weight of the MLP directly. And we remind you how important it is to make VeLO lightweight, since it must do an inference step for each weight of a neural network during training, so its speed directly affects the training speed of the target neural network we aim to optimize. The authors train VeLO to minimize the training loss at the end of the training of the target neural network. Yes, and by this we mean that an entire training run of the target network is one data point for VeLO. So getting VeLO to train and to converge is not a cheap task at all. The authors need roughly 4 weeks on 1000 to 5000 TPUs, imagine that. But remember that VeLO, once trained, has no hyperparameters to set, because the whole idea of this learned optimizer is to figure out by itself what the right strategy for each training step, model and task is. So the authors argue that VeLO's training cost is minimal compared to the amount of compute one saves for not having to train models multiple times to find the right hyperparameters for optimizers. So how well does VeLO work in practice? The already existing benchmark the authors could use to test VeLO on was the ML Commons workload, where on 5 out of 6 tasks, VeLO performed better than the Adam optimizer, which had a hand-tuned learning rate schedule and weight decay. But to have a more extensive benchmark that the authors and future work can use, this paper also proposes the Velodrome benchmark that encompasses 83 tasks. The idea of these tasks is to be cheap in terms of training time, so one can test quickly, thus the 83 tasks do not need longer than an hour to train on one GPU. The other thing is that these tasks should cover a wide range of architectures such as convolutional networks, autoencoders, ResNets, recurrent neural networks, and transformers. The good news is that VeLO performs really well on these tasks, even when compared to powerful optimizers such as NADAMW that had hand-tuned hyperparameters from more than 1,000 training runs. So VeLO that does not have any hyperparameters could outrun NADAMW out of the box and get better performance in 85% of the cases. And it got there faster than Adam. And on half the Velodrome tasks, it was even 4 times faster than Adam. But these good results on Velodrome are a bit expected, since the Velodrome benchmark contains exactly the kind of settings that VeLO was trained on this variety of architectures and short training runs. So unsurprisingly, VeLO's limitations are at long training runs of more than 200,000 training steps, or for large models that have more than 500 million parameters. So it fails exactly where hyperparameter search becomes more costly, in long training runs and on large models. But at least it means that VeLO can help in the most standard applications, which are also the ones needed more often in practice. And that VeLO underperforms in large training regimes is not necessarily the end of the story, but makes us hopeful for the future, where TPUs won't start screaming in panic that a single data point for a network is the entire training run of another network. So there you have it. This was Miss Coffee Bean's summary of the exciting VeLO paper that proposes to train optimizers from data rather than hand-tuning hyperparameters. Thanks for watching and see you next time.
Okay, that was a fairly short video, wasn't it?
Yeah, of course. So I was surprised. I mean, in one of the charts, they used 2 square as the improvement instead of putting it 4 times. And I was wondering why they chose to like 2 square times faster.
What chart
That's it.
are you looking at?
Yeah, it was in the video. I'll have to open it up. Give me a second.
Okay.
I think that one is, I think, out of the paper.
Yeah, I'm looking at the paper. Paper's long. What, 100 pages?
No, I didn't go all the way through. Wow.
Yeah, of course, you only need to read the first 20 or so because the rest are all references and then the author's contributions are a good 60 plus pages of it.
Yeah, it's figure 1 itself.
Yeah.
On page 1.
Hey, it's silly.
Silly.
You're muted, Dave.
I'm alive.
You're
Hey,
alive.
that's good news.
Yeah. Good to meet you. It
It
is. Nice
Yeah.
to meet you as well.
Yeah, Dave is the founder of this motley crew or whatever we are.
Sorry to be gone for so long. I won't be able to stay for the whole time today, but I did want to let you know that I'm alive and I plan on attending next week. So
Cool. Cool.
both of those things are cool. Yes.
Yeah, those. And you survived the rain.
And yeah, oh my God, thank goodness. Before I've been out for like 8 weeks, 6 weeks. And so I spent a bunch of time prepping the house, so I didn't have to do anything drastic during the rain. Thank goodness.
That prepper attitude of yours is paying benefits.
It's a nice bunker that we live in. Yeah. Don't let me interrupt though. I just wanted to check in though. Thanks, guys.
Cool, man.
Yeah, we got a nice eclectic group here, like bunker, person on the road. All that. Nice. So yeah, it's figure 1, page 1 of the
Yeah. The
document.
paper.
Yeah, of the paper. Yeah, document paper. Yeah, I don't know why they chose that language, which makes it. Yeah,
It's a logarithmic function is all, isn't it?
Oh, okay. That's what they're trying to point out. Okay.
Yeah.
I didn't see that left part. I just read
Log
that.
scale.
Then 2 square times faster. Like, that's the first. So,
Yeah.
yeah, I mean, they could still have written 4 times faster, which is much easier to read.
But not as mathematically well. It wouldn't match up with what they have on their scale, right? So
Yeah,
It's kind of a difficult graph to read. I thought it took a little bit of, you have to go through the details to kind of understand what they're saying. That it's basically, there's lots of tasks. Some tasks it's much faster. Half the tasks it's 4 times faster, and it's always a little bit faster relative to Atom. Although, what is that brown one? N Atom W, which I don't even know what that is. Sometimes is better, but
Oh,
on some tasks.
yeah. But in general, it's faster. And this is your typical Google paper too. If you read to the top of the page there, it says Meta trained with approximately 4,000 TPU months.
Yeah, yeah.
Yeah. Let me put that on my credit card. No problem.
Well, and given that, it must have been pretty disappointing to come to the conclusion that it works well for small, short training cycles, small network short training cycles, but not for the big stuff.
Oh, is that true? I hadn't seen that.
Well, that's just what it is. That's what they said in the video is all. I was
Yeah.
keying off
Towards
of.
the end, yeah.
So I guess it might be like handy for us, but when they're doing big stuff,
Uh-huh.
then it maybe not so. I don't, has anybody looked to see if it's available in a PyTorch implementation?
Don't know, but it is from Google. So
Well, the reference one I think was, yeah, here it is. Somebody, the standard one I think was
was it
really
in Torch?
Jax, isn't it?
Was it JAX? Then yeah, that's the extension language that TensorFlow has. So.
Yeah.
And was written by Google Brain folks, or devised, or however you want to call it. Just trying to see here. Maybe we can go through. Has anybody had a chance to look at any of these graphs are interesting. Sometimes I was just looking at these and they're focused on these like super minutia detailed things, but I suppose I'm not into this enough. Maybe, I don't know.
I didn't get a chance to read the paper, so I don't really.
Yeah.
So just from the video, I'm afraid.
Yeah. Yeah. I just thumbed through it. As I said, it's 100 pages.
Yeah.
Yeah, but it
what,
would be good to go through this in our meetup, like maybe more prepared with the paper. I'm just suggesting. Math heavy as well, but still.
Yeah, it is. Well, I don't know. It's not super math. Well,
it's got lots of stuff, but is there?
Yeah, I'm looking here.
Like they're just showing all the different types of networks and tasks and stuff like that they have to describe.
Yeah, and then the performance on it. So
right.
Yeah. I love this in 4.41. Scaling to models with more than 500 million parameters. Because yeah, my work was always that big.
But it did sound like when they listed the number of things that fed into the network, I forget the two terms that they use, but that they have the LSTM, so that's getting a time history of stuff, right? The different parameters. But didn't they listed the gradients, the weights, what was it, a couple other in there. So it sounds like from a memory footprint perspective, it's actually, it's not going to be lighter than Atom, for instance.
No. And yeah, so the four things, there were the gradient square, the Hessian,
right,
weights, and the loss, and maybe one more parameter, I don't recall. Yeah.
So I forget how big Atom is, but I thought Atom was like 3 or 4 times bigger than your parameter.
Yeah, it's 3 times at least, right? Because for each weight you have the beta, which is the well, that's a fixed percentage, but you have the momentum and the running average or what, which is momentum,
right?
And then one more value that you store, the last weight or something. I'm trying to recall.
I mean, one more variable you have to carry around with you.
Yeah. So
and compute potentially, right?
To compute the next weight.
Yes, another parameter to compute the next weight. Okay.
Yeah, and yeah, I hadn't even peeped into the paper, and when I looked at it, it is not at all math.
Yeah, it looks to be more just descriptive.
Yeah, but it has a lot of researchers, a lot of experiments. So it's highly empirical, and I wonder, like, it's like the new generation of empirical results now. Now that people are trying to tackle the understanding of neural networks with maybe some math approach, but like the other day, I saw another paper where it was all empirical results on. It was just yesterday. What was it doing? I'll come back to it. I'm forgetting it, but my first thought was that, well, it seems to be all empirical and oh yeah, it was so when you have multiple tasks, like in language models, for example, you want to find the toxic words and you want to remove that in your newer task. So if you train on different tasks, then empirically they prove that, well, if you fine tune on task 1 and fine tune on task 2 and so on and so forth, now if you want to combine all of those, you don't have to do training all over again with all those tasks. You can just add the task vectors is what they define. And they found the results to be way better than any fine tuning could get, more or less. Which also meant that you essentially, if you're working off some base model, let's say CLIP or whatever it is, and you want to, you don't have to train CLIP for, let's say, non-toxic language. If someone else has already trained it, take those weights and use the task vector and add to your model. And you'll get that without knowing how it was trained, the data set or anything, assuming they did a good job of training it, fine tuning it. So as long as you can get you start from the same base model as they did, all you need to do is get the task vector and incorporate that in your model. The point that I'm trying to make is that the empirical world of the next level, like in this case, the hyperparameters optimization, if you may, or auto ML, whatever you want to call it. In the other case, auto learning, different tasks, or learning once. There was this YOLO. You only
look once is what I believe.
Once, in this case, you only learn once.
Learn once or look once? I thought it was.
No, that is look
That's
once.
the new one.
Yeah.
Yeah, I'm just saying you only learn once, and then you can.
Oh, I see.
Yeah.
You're going to.
Yeah.
Okay.
It's amazing. I mean, I'm super thrilled that it's just accelerating this whole world of applying machine learning. It's more than exponential is the term, but yeah. It's more than exponential that we are used to.
Well, as I said, as we kind of started out, there seems to be a lot of change going on in our little corner of the world in the last year or so. So this being yet again another one. The question is, could you do this on reasonable size hardware? Not to me.
Yeah.
It's one thing if you have a multi-billion-dollar corporation giving you these resources, but how valuable is it if you're a graduate, PhD candidate or something like that?
So that's another good point that you make. There's a lot of research going on and trying to reduce the model size by quantization. So more or less, what I'm hearing is that floating point 16 models are becoming commonplace now. What that means is that now you need half the memory footprint. So
or a fourth, right? If you're going from inside, which variant of floating point you want to start with, right? So,
I remember 20 years ago when the the PS1 came out, and you look at the gains over the last 25 years over the PS1. I mean, you give if you had a PS4 and gave it to somebody 25 years ago, I mean, this is like, the CPU horsepower of, national laboratory or something like that. So, I guess we just have to wait it out for 20 years. And
that's the question I think that Deb was addressing, is maybe we don't have to wait it out. If we can be smart with our variable size, or
actually, this brings into something, during the 30 years ago, during the Cold War, the Soviets obviously had much slower computers, so they emphasize having higher order algorithms. For example, you know, Runga-Kutta. So, you know, you have a Runga-Kutta, you know what a Runga-Kutta is, a differential equation, fourth order differential equation solver, where you can have a, you know, fifth or sixth one. So, you know, you get the same results by packing your brain power into an algorithm that's, you know, harebrained, more complicated than the previous generation, and you get exponential increase in performance, not by increasing your CPUs. You know, you increase the complexity of the algorithm at which it works.
Yeah, that's interesting. I mean, these guys, you know, and once again, I think it has to do with the fact that they all work for Google and have like infinite horsepower kind of behind them.
You know,
that
one of my friends,
an easy thing to fall back on. It's seductive. Let me put it that way.
actually, one of my friends used to work at IBM. He was a quantum chemist, and you know, obviously IBM builds huge computers, you know, for national level, you know, big laboratories. And so we were working actually on blue gene light, and he said, well, you know, the big interest was in DNA folding 20 years ago. It still is, but you know, that was the big topic 20 years ago, DNA folding. And he said, you know, they had this program which would basically model various systems using like a ball spring method, which was good for estimating the boiling point of temperature of, you know, liquids and freezing points using a ball spring model, but not for DNA folding, because DNA folding takes into effect, you know, all these quantum effects and whatnot. So it's a lot more difficult a problem. He goes, well, you know, IBM salesmen are like this guy who's comes across a guy and he's looking for his keys. And he goes, where'd you lose them? Oh, I lost my keys back in the alley over there. Well, why are you over here? Well, the street lamp is over here.
But I was actually thinking about this similarly to what Walter was just presenting, or Walter, pardon me if I pronounced it wrong. Well, number one, right, you brought up IBM, which is kind of interesting because IBM was in the news today for propping up their AI offering using mainframe cycles, which is exactly kind of the trade-off, right? Like you need to do it intelligently, or you can just do it brute force. And I think, you know, if you look at, it'd be great if Shalom were here to comment on this, but like, if you look at the trend right now, where we are winning currently and where the slope does not appear to be slowing down is essentially empirical without any theoretical foundation. And eventually that slope, you know, we've been predicting that slope would curve over for a while, and we've been wrong. So I think all the evidence suggests that we'll continue doing that basically until the empirical gains require new theoretical science, at which point then we'll be forced to make more intelligent theoretical models so that we can get participation from academia. But so long as we continue to get like these step-fold 2 to the second power improvements, you know, from empirical only type experimentation and results, I would personally forecast that we'll see some academics trying their best to do it, but that the driving force will be innovation, and we'll continue to see more and more complex models so long as that's supported by the results.
Sally, do you think it's solely theoretical that allows us to improve that, or if we just change our metric? Right now, our metric is, you know, accuracy of the performance of the model, et cetera. If we change the metric that we're trying to optimize to be performance per kilowatt or whatever, or per dollar.
Sure, but there's no outside force
right now. Yeah.
So the primary outside force that's motivating the current pace of innovation is, you know, as it's coming from commercial entities that are, yes, kind of struggling to justify their AI investments, but they're making such massive shifts that they continue making them. Even in the midst of layoffs, we didn't see a massive layoff of PhDs from AI research at Google, right? And I think that's probably the most indicative thing that I would say is the biggest driver. As long as commercial enterprises see a 5 or 10-year arc to billions of dollars, that will continue to see the machine that's generating the fastest innovation, i.e. right now, entirely empirical methodologies, continue to absorb the time and energy of those enterprises.
Yeah, I agree. I guess I was just making the point that I think it's, you can get I would suggest you could get empirical or empirical optimization of the performance per dollar, performance per kilowatt, not just theoretical.
Yeah, I mean, it would still be, you're right, that would make it a practical thing, but without a practical motivator, right? Like if Google were cash strapped, then or energy strapped, right? If they didn't own their own dams in Oregon to generate their own hydroelectric power, right? Then maybe that would be a motivator. But at whatever it is, 0.7, I think in hydroelectric in their owned is 0.7 cents per kilowatt hour. I mean, that's pretty difficult to then go to them and say, all right, let's slow down the innovation curve in order, the gross innovation curve in order to optimize for this other variable.
I'd heard some.
And not only that, the other side of it is, sorry, Roger, just want to make a point on this, energy curve. So the other side of it is they are heavily investing in how to optimize energy production from whatever, whether it is the what is it called, the windmills, and what's the term that we use for
hydroelectric dams.
Yeah,
the fan list.
Not burning coal and gas, what is the term? Like
renewable.
Renewable. There you go. So, a lot of, using AI in turn, building models to accelerate that. So in some ways, it's like like the nuclear fusion, right? I mean, how to control the nuclear fusion, those arms or whatever those were there, right? So
the lasers, yeah.
But if you look at the reason for that, that's because that's applicable across their entire enterprise, right? That's applicable across $500 billion a year of spend in electricity versus optimizing. Yes, 4,000 TPU hours seems expensive to you or I to put on our credit card. But when you look at it in the vast budget of IT at Google, maximizing the value of that, probably call it $2,000 spend, is nothing relative to if I can get 5% more efficiency from all of my turbines. That's huge, right? That you're optimizing where the denominator is in the tens or hundreds of billions of dollars, right, versus optimizing where the denominator is in the couple of million.
Yeah, right. and that that is their largest cash cow, right? Or their second largest cash cow.
And by the way, there's also a trickle effect. So it's not just Google benefiting from it, because Google will maybe focus on the space that it is focused on. It will venture into other areas through DeepMind and whatever else. But at the end of the day, there will be a lot more other enterprises that will leverage these technologies and build products which will accelerate in whatever fields they are. Like AlphaFold has accelerated this whole pharma industry. It's not that Google is only benefiting from it, right? So
yeah, and AlphaFold, do you remember what I remember the leap they made was, considerable between previous attempts to do the protein folding type thing. They jumped 10-15% or something like that.
30+%. So
30 plus. Yeah, okay. I remember just being shocked at the advance.
So the first version that they released in CASP, which is the computation for protein structure prediction, they were the topper already in the 13th version. Before that, because of the new structures that would come out every 2 years and new algorithms will continue to fail, going past beyond 40% accuracy. So in 2018 or 20, whatever that year was, 2018, I think, when Google announced AlphaFold 1, they were already 60+%, and rest of the gang was still at 40% or so. And then in 2020, CASP 14, they were 92% or something, and rest of the gang was now catching up with Google's AlphaFold 1 non-release code, but the theory shared, like how they did it. So some people were catching up to Google's AlphaFold 1, but AlphaFold 2 was already like 90+%. And for all practical purposes, the organizers of proteins, the CASP computation, announced that this problem is solved now, because 90% is what they consider as solved. Like now you're like, going much deeper, which is like, okay, now you're like any other domain, for example, right? The problem is solved. Now you're trying to put like in our Chat GPT, for example, right? The problem is, you can say it's solved. Now you're trying to figure out the guardrails and how to make it more non-toxic and more less biased and so on and so forth, right? In
those are optimizations on a base technology then.
That's right.
Yeah.
So, but in no time after that, all the human protein structures were published. Now someone with some accuracy levels, which are pretty high. So, once someone goes and tries to confirm that, is this a structure, it will, for 90+% or 95% accuracy, this is what it is, right? Which is a big deal because now you can focus on drugs, you can focus on next level of protein interactions, like multiple proteins or the polymers and so on and so forth. So, it's binding, like how they bind with each other, predicting the binding sites, ligands, and so on and so forth. So essentially, the leap that happened is not just finding the protein structures, but the downstream tasks have just accelerated in leaps and folds. And not only that, then it triggers innovation. Now it's an optimization problem as well. AlphaFold takes these many resources and solves it in this long. Comes Facebook, says, well, we have ESM-fold, which is way faster if we change the MSA, the first end, the initial part of the AlphaFold, instead of using the way MSA was, and I forget already, I did it 1.5 years ago, like how they solved for MSA optimization. They said, well, we'll use it as a language because it's a sequence essentially. So we'll try to emulate it as a language model and then see if that will help. And that helped accelerate the initial part of folding. They compromised a little bit on the accuracy, but then as well, that instead of taking 2 days, for example, it takes now 2 hours. So we can validate the ones that we call later on that, okay, with AlphaFold, we can spend those 2 days, 10 days from now, but in those next 10 days, we can use ESM-fold to accelerate our findings. So the point is that one thing leads to the other, to the next, and boom. It's like the whole pharma industry is right now like figuring out, or I wouldn't say figuring out, but to Sally's point, just like how Google is investing a lot in AI, and AI PhDs are intact and accelerating, and so is happening in the pharma industry. All these bio. This is the other thing. I'm sorry, I'm going on a rant here. Some kind.
It's a good rant.
It's a random forest. It's more of a random forest.
like if you think about,
are we coming to the Leafs or
the pathologists and radiologists jobs, right? Like looking at the scans, right?
Yes.
Any of these Kaggle competitions, that the people who win those competitions, none of them are from the biology background. They're all some computer scientists working or AI engineers working at H2O or some company in Belarus or somewhere else, and they don't know anything about biology of it. They read it up and then see, okay, this is how the 3D structure is, and now how should I model it? Because essentially it's in CT, it is slices, but it is not really 3D. So you have to somehow come up with the 3D structures based on that, and then find the fracture or find, you do some basic learning, which is like maybe 1 hour. Maybe I'm trivializing it, but let's say 5 hours of time to spend to learn.
But you're not going to become a molecular biologist to do this.
You're not becoming a molecular biologist or a radiologist or a pathologist, but you have data and you just throw some model at it, and then someone has said, well, for this model, if this is the prediction, then you're accurate, otherwise not, and so on and so forth. Right? It has labeled data. And
well, we've kind of come back to where I think Sully was on that, right? Which was, you're not looking at the science behind those. You're looking at data and how can I brute force almost. I won't say brute force, that's probably a bad thing, but how can I process that data to get the answer I want? But
I want to interject at that one. So the science, what is science? Science is the chain of thought, right? Based on your memory and experiences.
Yes.
Right. So reinforcement learning based on your experiences and the memory that you have.
Right.
If you look at the latest LLMs, the large language models, ChatGPT or otherwise, one of the recent papers that was also at NeurIPS and has been discussed recently is emerging properties of large language models. And they found that once you reach a certain threshold of parameters, after that, the model is able to learn with very few short, maybe even 1 or 2 short examples of solving some complex problems based on the chain of thought emulation. So you give it a problem and say, okay, this is how I'm going to solve it. This is first thought leading into the second thought, leading into the third thought, and so on and so forth. You give it 2 or 3 examples, and then you give it another complex problem of the same domain, which it has never seen before, and boom, start solving it. So the point is that discovery of science, or what Sally was talked about, I think that's going to accelerate, and if not in automatic way in the beginning, but pretty soon, I wouldn't be surprised if you throw it some complex math problem or a physics problem with data, and then based on the experiential information as well, this worked and this did not work, and then it will apply that chain of thought to say, well, this is what I think is the let's say the abstract model for gravity. I'm just simplifying it, but so I wouldn't be surprised if that also materializes, and if not next year, but in next few years.
So, and that breakthrough you think might come from somebody more in deep learning and machine learning versus somebody that's a theoretical physicist or something like that.
I think the scary thing about what Deb just said is that it won't come from someone at all.
Yeah, but it'll come.
The scientist is doing the reinforcement learning, and who's the scientist? The scientist is in fact
the model itself. Yeah, good point.
Right. That's a pretty intense freaking claim there, Mr. Dev.
Yes, but then some of the open problems like Knott's theory problems.
Oh no, I've been watching this. This is I'm 100% with you. It's just an interesting the way you formulated it. It reaches the conclusion that the statement, the person who discovered it, is not a statement anymore. It's not a valid statement anymore because the person did not discover it.
Yeah. And same goes for like the alpha tensor, right? The one which optimized the matrix multiplication. It's not that they solved they did solve the problem by optimizing.
Yeah, 100%.
But see what happened as a result of that. Some other mathematicians said, well, we never thought of this. We thought we don't need to optimize it. 50 years ago, we put the problem to rest. And now that alpha tensor has given us a way to optimize it, well, maybe I can reduce one more operation. So now that can feed back into alpha tensor, and so well, let me see if I can optimize it further based on this.
Again, I think it's wonderful for science generally. I think that the part that's hard though is you have to accept that there's a new party in the science, right? That the model is in itself as important as the scientists, and it's a cycle. They can feedback on each other, but it's much more the model than the scientist, than the data scientist, the AI engineer actually did that discovery.
So I mentioned before you. Sorry, Jerry, I've been talking about.
No. This is a very interesting discussion because I think it gets to the heart of the questions. And somebody was talking, about ChatGPT and what is it? The astrophysicist,
NDT, Neil deGrasse Tyson.
Neil deGrasse Tyson.
I'm going to mention him right now, but go ahead. Yeah.
Maybe that's what he is, thinking about. That if this model is smart enough, rather than having, theoretical physicists look at this, or, astrophysicists, theoretical astrophysicists, man, that would be a really narrow field. But if you're an astrophysicist, I guess your theory anyway, mostly. But, maybe they would just use a tool and put forth constructs and see which ones are make sense to the machine or the thing, whatever you want to call it.
Or maybe not, you just throw everything to it and it will figure it out. Well, based on your experiences that it learns from that. You don't even need to tell it anything more, maybe.
Yeah, maybe you define the box and just let it go at it or something like that.
I mean, the only thing you tell it is, well, I think this didn't work and I don't know why, and let it figure it out why.
Yeah, I'm curious, kind of what's the difference between, Dave, Sally, you're using the idea that it's the AI that discovered something. The other way to look at it is that the scientist used a new tool, which was the AI, to find a particular pattern.
Well, the specific point that I was hinging on was that Dev said, what is science? And science is this reinforcement learning process. Mm-hmm. And so if the scientist is the person that does, or the entity that does the reinforcement learning, then if the model happens to be a self-feeding of some form reinforcement learning model, then arguably the scientist being the entity that performs science would then be the model.
Which is the same concept as Sparrow is, or ChatGPT is also adopting, which is reinforcement learning based on human feedback. So it's getting smarter based on human feedback. And right now we're talking about language. Very soon we'll be talking about science that way.
Interesting.
I mean, that's the one that we did last week. And to NDT's point, Neil deGrasse Tyson, NDT's point, I mean, I'll share that podcast clip. It's like maybe around 20-30 minutes. In the beginning, you're like, so what? People always think this time is different. But then the more he got involved in the conversation, you're like, yeah, maybe UBI, the universal basic income or something will make sense. And it was a pretty fast transition, I would say, for a person of his stature and clarity of thinking to give in.
Well, not to go off on a discussion of that, but you talk about UBI, yet people don't talk about the fact that we spent something over $35 trillion to bail out the banking industry back in 2008. I mean, it's like good, but I don't want to be on the hook for that. It's like the wrong people got the money. I mean, if you believe in capitalism, then let the chips fall, and the people who made the investments have to lose their money in order for basically it came down to a question of no one really loses in an economic system. It's just money changes hands, and the wrong people ended up with the money. And it's like, well, that's not my problem, and it's not the part of the government to go and make these banks whole. Okay, no one forced them. It's like oh well, the banks knew what the hell was going on. They just knew that they could milk the government to go bail them out. This is not a new story.
Yeah, the only counter to that I hear you, and I totally understand your point, and I agree with many of the outcomes that you're talking about, except one important outcome, which is if the whole economy, if it's a cascading effect and starts from the top and it trickles down to the bottom, then the biggest loss is in terms of the productivity. And the only way that you actually increase your value for the money is by improving the productivity. But if you lost the whole ecosystem of being productive because of letting fail some big...
But other businesses would have come in there and bought out the assets to the losing parties. So, that's just part of the system. I mean, there's a lot of losses. You talk about diversity. We're destroying the ecosystem, and in some ways, that's going to come and hit us because we're destroying the web of life. And it's like, well, okay, so
that's right. And only counter argument to that would be like, should it be disruptive blow like that, or should it be a managed?
Well, listen, the big problem is that you're having money influence government in a way that it was never designed to. I mean, when you have a democratic system, you shouldn't have that level of influence of money. I mean, you're back to a feudalistic system where the king decides who's right and who's wrong and who's going to get bailed out, and just rewrites the laws.
Right. So again, I'm not saying anything against what you're saying, except for the only other points. Like there's only one other point, and that's the only one other point.
Well, but that's because people with money feed that narration all the time. People with money feed that narration. It's like, well, what about my business that went under in 2008? No one came to bail me out.
Yeah.
Probably you're right. I mean, there is a new law that is, I don't know if it is either passed already or in the process of getting passed, the anti-competitive law or something. I don't know if you've heard about it. So previously there was this huge inhibition, if you may. You cannot leave a company and work on the same idea because of the anti-competitive laws or something like that. And I think they're doing away with that because big companies have become too big, and innovation is in some ways either limited or stalled because of that.
Well, that's because, it comes back to, I remember 20 years ago, it was a some tax code that would limit contractors to not getting their sole income from one corporation. so if you're a computer consultant, there were laws put in to basically thwart you from getting your income from one client. Well, you look at law firms. I mean, there are lots of law firms that just make their money from law, just servicing one client. And why the hell, if what's good for a software engineer should be computer consultant should be good for lawyers and marketeers too.
That's probably why it's gone now, though. I mean, you can, as a consultant, work for a company. It used to be you had to move, right? I don't know if you remember that, Walter, in the day. You couldn't, there was this definition of what's an employee versus what's a consultant.
Yeah.
If you stayed too long working at company X, you were really not a consultant, so you couldn't write all that stuff off from the business side. Plus, they could not get by without paying you benefits, accruing, retirement, all that stuff.
Right.
So that got kind of thrown away.
I mean, when I worked as a consultant, okay, the money was good. I mean, I was getting,
Oh yeah. We had a consulting company with 30 people. So yeah, it's a good way to make a living.
But there are, like, for example, I know the whole process, like pizza delivery guys weren't considered employees. They basically were considered independent contractors. So they would buy pizzas from Pizza Hut, deliver it. And then after the delivery, they would sell it so basically they would buy pizza from the Pizza Hut, they'd deliver it. And then if they couldn't deliver it, they could sell it back to Pizza Hut. And so it's an artificial thing to basically, motivate young 17-year-olds to risk their lives to deliver a pizza in under 5 minutes.
Well, maybe we ought to steer this conversation back to that's okay. No. It's good stuff, because all this stuff, we did get into this thing about UBI, and when you think about why you need UBI, it opens up a lot of things.
Well,
Hey, Dave. Dave, I was going to ask a couple of questions from your comments. One, you had mentioned protein interaction. Have you seen or read any papers on, an AlphaFold type of approach to multi-protein interactions?
I am so sorry, but I've not. Even if I have looked at the headlines, I have not read the papers in detail.
Yeah, it seems like a natural progression to me, and I'm curious, what type of progress we're making on it. But that's okay. Sally, you have one?
I'd be super interested in that as well. I mean, there's all your cancer drugs, right? I mean, that's
everything. Yeah,
everything.
All medicine there. Basically.
Yeah, the whole drug discovery business is going through, what would you call it? Kind of a what do we do type moment or things like that. They're having some issues. My daughter happens to be a manager in that, and she says they're having real issues with certain things
related to AlphaFold type of
not necessarily AlphaFold, but just other technology too that is not necessarily machine learning based, but process based, things like that. That things that they used to do one way are now changing, and it's questioning, did the way we do it and we historically have done it, is it the right way to do what we do?
Or is there something better?
Yeah, is there something better? Are we worrying about the wrong problem? That sort of thing, fairly substantial at the lower level.
So, Dave, the other thing sorry, Sally, you had something?
Nope, I punched it on accident.
Okay.
Oh, okay.
The other question I was going to ask was, you mentioned this idea of kind of presenting a solution to a model, I think language model, and then you applies that methodology to a new problem. Is that something, I'm interested in how that works, and just wondering if you have any papers or any references on that.
Right. That's a paper called Emerging Properties in Large Language Models or something like that. It was presented in NeurIPS, but these days there are longer presentations and hour-long presentations that you can find even before the actual conference. So there's a long 1 hour long, very good talk on that. And if you want, we can, if you prefer, we can cover that at some point in time. I can find that to you. That's actually not
I'd be interested in that.
Yeah, that's more on the, just like this paper, more on the outcomes heavy, that, okay, this is what we did, this is where the turning point is, and there are 3 different stages. And first stage, it is memorizing. In the second stage, it is learning for this task. And in the third stage is when it has learned to learn from the few shot. So, but then there are those thresholds that they identify, and they say, well, these are the large language models. That's the reason they are able to generalize, because they have some threshold beyond which they have this huge bump in their generalization performance.
Okay.
Now, in terms of theories, I mean, we are still scratching the surface with understanding the neural networks.
Is this one of those things where you just empirically achieve this sort of thing, and now we're focusing on why we achieve that sort of thing? Or
so it's somewhere in between. So empirically, we saw that, well, suddenly these large models are able to generalize. So then the second level was, when are they able to generalize? Is there something more we can learn? So it's about, like, can we learn something more about when they are generalizing? Not so much as how and why they are generalizing. So it's like, oh, this is the threshold for these models. So once you are beyond this point for these kinds of models, this is when it is starting to learn for this task only. But the chain of thought is like learning from new, like few shot learning, right? When is it that happens? But what's
few is your question, I guess, right? In that
but
context.
very few, like maybe 2 or 3. I mean, this is really amazing. And it is, see, the thing is, you figured out, or you saw that ChatGPT is doing amazing. Everybody knows that now, let's say. Yeah. What is the threshold when it starts doing amazing? So that's the study if you made. So that's like emerging properties. When do they start emerging? And what are those properties that emerge at different thresholds? Not so much as why did they emerge now? Like, can we? So
so we're seeing this behavior, and then we're working on the behavior we're seeing, not what is the mechanism behind the behavior yet.
Right.
Eventually, we will probably get to there, I assume.
Right. For example, if I sow a seed, I'll get a tree. But then, well, if I sow a seed in spring, then I'll get a tree grow much faster versus if I sow a seed. And so it's learning that kind of thing. But, well, why does it do? Well, because it absorbs the nutrients from the soil and all those things. It's like way advanced theory.
So if you want to post that one, reference that in the spreadsheet, that I at least personally would be interested in that.
I think I would too. And I think it sounds like Sully was, I don't know about everybody else. But
there was another one, we lost Ted, but he had mentioned last time, what's it called? Anthropic.com.
Right. Has anybody else? I heard something about them and I don't.
I just, it's anthropic.com is the website, and I went there and it looked like a lot of several very interesting papers in there.
Okay. So these were the AI safety guys and things like that. Right. Whoa, Walter, your picture has gone wacky, man.
Oh,
or something.
My CPU is overloaded, I guess.
Oh no!
I was typing on my Google Chrome, and I guess that's just a power hog.
Okay. Anyway, you just had something really interesting going on there.
They had a paper on that kind of, at least the title caught my attention, was on trying to understand explainability, looking at reverse engineering a single neural network. So it's another, I thought that was another area anyhow that if people are interested, we can look through some papers in that area.
Yeah, I definitely was. We had in the Google GD program, we had kind of this explainable AI series going on. It's pretty interesting stuff, trying to do that. I didn't spend as much time as I should have in that, but we could, if we want to look at that, I'm all for that too.
Did you have material from that or?
Not really.
Okay.
Not really. And that's been like 3.5 years ago. So I'm sure the, SOS state of the art has moved down the road a bit, because there are a lot of people that are, getting their PhDs and things like that and addressing the explainable AI issue type thing. And it would be interesting. I don't know if other people, I think ChatGPT may force the issue, to some degree, you know, because
Yeah.
people are going, how does this work? Is it taking, you know, and then, you know, from the newscast, you know, it's going to take your job, blah, blah, blah.
Right.
But, you know, but, you know, if you need to understand how it works before you make a statement like that, that's, you know, beyond just a very surface level type thing.
Right. Yeah.
So anyway, yeah, explainable AI, I think is a big thing, because as we see things like ChatGPT, as you know, all these new tools that we're building, people are going to want to know why, you know, why did my bank loan get rejected, you know? And it can't just be, well, the algorithm said so. That's just not going to work.
Right.
So,
Right. Hey, Roger, I just posted the link to the video on the Zoom chat.
Okay.
And the paper, and it is presented by one of the co-authors who happens to be an undergrad at Stanford, I think, and subsequently at.
geez, he's an undergrad.
Yeah.
I'm feeling stupider and stupider every day.
Well, it's a matter of time that every one of us will say, God, AI, can you?
As my college project.
Yeah.
I mean, oh my AI, not oh my God.
Yeah. Oh my gosh, this looks like the group I tutor every 2 weeks over at JPL. So they all look so young. Oh,
I think our calendar's open for next meeting.
okay.
Is that one that we'd be interested in following, that one, the video that Dave just posted?
Deb posted. Yeah. Can you paste it in? I think that might be useful. Walter, you seem to have a little bit of interest in that area, I guess.
What do you mean post it in, Jerry?
Into the
into the schedule. Yeah. I'll do that. I'll update the meetup
with the link to the paper.
Yeah.
So
Yep.
Okay. Interesting. All right. So we're getting close to time here. So maybe we ought to wrap this up. Anybody else have anything that they'd like to contribute to the conversation? Three of us have been doing a lot of chatting.
Yeah. Alan, Janeth.
Can we look at this video next week or something like that?
I'm sorry, Alan, what was that?
Can we watch this video next week or something like that? Or is there a paper connected to this one? Emergence and reasoning in large language models?
Yeah, I think that's what we were proposing is we'll watch that next week. And it's an hour long, right? So it's probably going to be 2 weeks worth.
Yeah.
Or maybe some highlights reel. Or some highlights.
Yeah. Although, you know, we'll have to take a look and see where we want to. You know, the pace we set is we want to make sure everybody kind of understands it. So we'll deal with it at that. It'd be better to take 2 weeks than try to cram. This looks pretty meaty. Just take a quick peek at it rather than trying to cram it in, you know, just for schedule purposes. Yeah. My 2 cents. But yeah. But Alan, so it should be is it on the calendar, Roger?
Not yet. I'll put it
okay. It will be on the calendar fairly soon here, and you'll be able to link to it and pre-watch or do whatever you want to do. Okay. Yeah. Okay. Cool. All righty.
Anybody else?
Yeah.
Any other suggestions, directions, inquiries?
Nope.
Deb, one other query I have for you is if the way I understand it right now, ChatGPT, its model is essentially all of the content is embedded into the full weights, right? What am I trying to say here? In one of the few shot papers we looked at a couple of years ago, I think, it had a separation of kind of the algorithm and the database, as it were. The knowledge and the algorithm were separate, which to me, it just resonated to me that it was more explainable, it was more generalizable, extensible, etc. And I'm wondering if there's anything that's going on right now that is close to that. ChatGPT, if I type in to ChatGPT, write an Enigma machine encoder or Enigma machine simulator, it can do it. But where is that knowledge of what an Enigma machine is? It's somewhere in the 75 billion, or no, that's more, it's 350 billion parameters, right?
It's probably more than that. I don't know how many it is. 175 was the GPT-3 model was 175. And Google has a model called Palm, which is 540 billion. So I don't know.
That's the part it seems like, how am I going to ever explain that? And also, how do I make it learn things quickly?
So I don't think, of course, I don't have an answer to that, but I will make some conjectures here. So there are some works that happen in recent past, which kind of try to understand that at the end of the day, these models, once they are learned, are nothing but some permutation of weights in the hyperspace. So depending on where, like you randomly initialize the weights and then you start training, and depending on the order in which you got the data set items and random weights that you assigned, weights start going in a particular direction and you got some fine-tuned model. You do this process again, random weights, but you randomize the data set injection, you get another model which is performing equally well, but they are not the same models because it's in somewhere else in this hyperspace and that model is somewhere else.
Right.
And then they try to figure out, well, can we then understand, is this just the weights permutation that happened here in some ways?
Yeah.
So where I'm going with this is that once you understand, well, this is the weight permutation that is happening, and not that something has happened concrete in that direction. It's like then trying to figure out, well, these set of weights are triggered for this data set over there, and these weights triggered for this training, during inference, these weights in the first model got triggered here. During inference, these weights in the second model got triggered here. Can we conclude something about the data for inference and those weights and say, well, if we keep giving the data of this kind, these are the weights that capture these properties, if you may. And depending on your model, however way you trained it, those weights keep getting shifted. It's like not like a human brain where you always, you have the frontal cortex and all the, it's predefined and same things trigger everywhere. These neural net models are still all over the place depending on how you initialize it. But can we isolate it and then say, well, there is always some portion in the model which is focused only on the language part or only on the edges part and so on and so forth. And we can tell that if we do multiple of those experiments, and well, this is the way I can say this is the frontal cortex and this is what it is.
Yeah.
I'm just, it's such a bad example, to be honest. I mean,
no, it makes sense. I mean, in terms of how would you get the explainability? Where did this come from? I guess I just feel like instinctively, I feel like there's a difference between learning a logic system and learning a fact, and that our model should treat those differently.
So in that way, when we talk about brain, right, do we know where memory is and where the computation is in the brain?
I don't know. I
So
don't think we have a great understanding of the memory.
Yeah, which is the same concept that it's all the neurons. Somehow they know when to call upon, or the way they trigger the weights that have been set when you learn something new kind of capture the memory of what you saw and the experience.
Yeah. I mean, I don't know enough about the brain to know.
I don't think even brain researchers know it.
Yeah.
At a certain level. No. I mean, if you look at, this thing being the total number of all the secrets, I don't think we're very deep down that pile yet,
And that's why
I just know it, like in that example of the few shot learning, the update mechanism for the let me call it database was different than the update mechanism for the logic part of it. And that to me makes sense, that if you want to be able to learn things quickly, quickly add in a new fact, that doesn't change things. But it took you a while. There's a lot of complexity. It's fairly stable about how do you think logically.
That's
yeah.
Sorry, go ahead, Jerry.
No, I think just, I think that's a good point, because if you memorize, an address or something like that, that's one thing, right? It's easy to store, but to apply, what that means contextually is a much more difficult problem.
Right.
But that's exactly the point that, with the size, this particular paper, that emergence and reasoning in large language models can potentially also highlight that once you cross a threshold, you don't need separate memory. You just give it a few examples. Just like if I see 3 examples of a new variety of cat, it's possible that you show me the 4th image of that. I'll say, well, that seems like the new variety you just showed me.
Mm-hmm.
I just saw 3 of those. How did I like put it somewhere in my memory, or that changed the way neurons triggered and so on and so forth, right? Versus in the past,
Walter's comments.
In the past, meaning in the AI world past, the models were small. They were not as big as 2 years ago, as big as the current models. So those properties did not happen, which means you had to, if you wanted to emulate memory and reasoning, then you have to create 2 separate modules, if you may. But with these large models, you don't need to, apparently.
Or that you're using that short-term context. That's the part that is kind of the update quickly, right? That you're providing a few examples and it learns it, but it won't learn it forever, right? Isn't that in the large language models? That's in the context.
So I was going to bring that point, but I thought maybe I'll just leave that aside.
Yeah, it's getting.
Maybe we should. We're over time now.
If I may, just the last thing is that, when you learn new things, forgetting old things is a very important concept in AI world as well. You train it on something new, and now you totally forgot and messed up the old thing. So how do you remember and retain both?
Yeah, that's a trick. Yeah.
Well, another area of interest. So if we find something in that area sometime.
Okay. To recap though. Yeah. Go ahead, Roger. That's where I was going to go immediately.
Yeah. So
what
next
are we
week
doing
we got something. I'll put it on the calendar, add it to meetup, and we'll have a week or 2 of this emergence and reasoning in large language models. How's that sound? Oh, good. All right. Thanks, guys.
Good. Thanks, guys. Everybody have a great week.
Nice discussion.
Bye-bye.